So in the last video, we learned how to convert from fractional base 10 numbers to fractional base 2 numbers, and we might think that's good enough because then we can represent numbers that are bigger than 1 and numbers that are smaller than 1. However, one of the other sort of advantages of floating point numbers is allowing us to represent really big numbers and really small numbers. So we're going to want to do more than just represent fractional numbers. We're going to want to represent exponents as well. So we're going to have to find some way to represent exponents in base 2, and there's going to be a bunch of different ways, and then we'll show you exactly how the standard that a lot of assembly languages use, which is IEEE 754 usually. So the naive representation is to say, well, we'll just store two integers, right? One integer that represents numbers bigger than 1, and another integer that represents the fractional part, numbers that are smaller than 1. We'll put those together, and that will give us our number. But that gives us a very limited range, and we're going to want a larger range than that. So floating point means we're going to allow that point, the radix point, where the number goes from positive powers of 2 to negative powers of 2, we're going to allow that point to float somewhere, not necessarily at 2 to the 0, right? It could be at 2 to the 5 or 2 to the negative 5, allowing us to have bigger or smaller numbers. We do this all the time in base 10. We use exponents, right? We use scientific notation to say that 1,000 is the same as 1 times 10 to the 3. And that 1 is 1 point something, right? 1,100 is 1.1 times 10 to the 3. Right? So we're allowing ourselves to represent large numbers or small numbers based on the exponent from the radix. We're going to take that radix, and instead of focusing it at 10 to the 0, we're going to focus it at 10 to the 3 or 10 to the 6 or 10 to the 9 or whatever. Right? So 1.5 million is 1.1 times 10 to the 6. Now 1.1 is just a regular fractional number, but instead of that decimal point being at 10 to the 0, it's now at 10 to the 6, and we notate that by saying 1.1 times 10 to the 6. We can do the same thing in base 2. We can indicate the location of that radix point using some external notifier. We can say this is, for example, 1100000.0 is by default that times 2 to the 0 because that's where that decimal point lives, that radix point. But we can also say that it's the same value as 1.1 times 2 to the 6. Now saying that this radix point represents 2 to the 6 instead of saying it represents 2 to the 0. So this is a standard representation, this is scientific notation, and we're just going to build that feature into our representation for binary numbers. So what we're going to do, we're going to invent a thing that's sort of like base 2 scientific notation. We're going to draw out a generalized number that looks like this that is going to give us access to any number that we want, any number in the real domain that we want, right? So we're going to have plus or minus, and what we'll see is that even though in integers we had this clever little mathematical trick called 2's complement that allowed us to store positive and negative numbers together, we're not going to be able to do that in floating point numbers because the trick doesn't work anymore if we're also encoding exponents and shifting the binary point around. The decimal point, the radix point, indicated where that negative column was. If you look back in the video on 2's complement, you remember one of the columns is negative, the rest are positive. But if we allow that radix point to change its location, we also have to allow that negative column to shift, and that's going to get very complicated and frustrating. So instead, we're just going to say, you know what? We're going to encode the sign separately, which was one of the ways we did that in integers, but now we're going to do that this way in floating point. So plus or minus the sign, this is going to be the sign of the number. We're going to store this as a single bit, and for consistency with 2's complement, we're going to say that if that bit is negative, if that bit is 1, then the number is negative, and if that bit is 0, then the number is positive. Then we're going to store another piece of information that we're going to call the significand. It's sometimes called the mantissa. We also will eventually call it the fractional part, as you'll see why in a minute. That stores the sort of numerical value of the number that we're looking at. And then we're going to store the exponent of where to put that number on the size of ranges. So if it's 1.1 times 2 to the 6, then that 1.1 is the mantissa, and 2 to the 6 is the exponent, right? 1.1 times 2 to the negative 6 is 1.1 millionth, and 1.1 times 2 to the positive 6 is 1.1 million. And that gives us 2 to the 6? No, those would be 10 to the 6, wouldn't they? Times 2 to the 6, this would be 32,000 or whatever it is. So No, 32,000 is 10 to the 5. 64,000 is 10 to the 6. Know your powers of 2. So we allow that mantissa to shift up or down based on that exponent. S is going to be the significand. That's the number that we're shifting. Then b to the power of e is some base to some exponent. Now, the base is almost always the radix, but not always. There are some floating point representations that allow a base of 16, for example, instead of a base of 2. That allows us to move that mantissa in chunks of value of 16, right? 1, 1, 1, 1, 2 to the power of 4. But it doesn't give us representation for every possible number, because you might have like 0.01 times 2 to the 3 isn't going to be representable. So it would be 0.1 times, or 0.001 times 2 to the 4, some other value. So that gives us a much wider ranges of exponents, but it changes the way that we can represent mantissas. The representation that we're going to use in MIPS and others called IEEE 754 uses 2 as the base, and it'll be really simple to understand. E then is our exponent, and we can use a signed exponent, meaning we can have 2 to the power of some positive number or 2 to the power of some negative number. And as it turns out, the way we do this, you'd think it's an exponent. The exponent is an integer. We can't have fractional exponents. Well, maybe we can, but in this representation, we're not going to have fractional exponents. So it might make sense to just use 2's complement for that. Well, as it turns out, we're not using 2's complement for that. We'll use something else. And it'll be a little confusing at first, but it'll be clear why we do this once we get into that. So this is a generic representation for floating points in any radix, in any number system. For base 10, we use exactly this representation where b is 10. In base 2, we're going to use a representation here where b is 2, and then we'll show how to represent s and e and the sign and everything else. So IEEE 754 is the generic system that we're going to use, and I'll explain it in more detail in the next video.